we have examined one from the industry source about how to use fans and so on. Considerable effort has gone into how to actually create a small setup by which you find out the system characteristics of a small enclosure. So, typically a system could be a rack which has lot of sub racks, which in turn has printed wiring boards or other things, and then you have power supplies and so on. So, then lot of it has been talked about on whether you need to blow it from the bottom or suck things from the top, and a little bit about filtration, and then idealized setup on a plenum chamber, and how do you find out what actually is the flow rate inside by putting a small U-tube manometer. Symbolically they have shown the U-tube manometer, because you can vary the pressure and you can I mean it is calibrated in terms of head and you can do it, and other side the actual system pressure and so on like that. As I have pointed out earlier, it is on a fully populated board. If you do it, it will be good. This is where initially in that same old slides they have shown about saying, why can't we have concurrent thermal engineering of electronic equipment. Yes, it is easier said than done. If you know that something is already there existing, you can copy it. Now, let me go back to a little bit of the what you call theoretical things once more, and you have a look at the fans and since things which I have collected here earlier. One of the things you will notice is we have two fans here. See this, we have one air circulator, I will show it like this. Similarly, I have one more air circulator here, and then we have a heat sink. Why this is all the more what do you call important that we notice this is, if you will now look at this heat sink, see this, several things come to our notice. One of the first thing that we come to our notice is, as you have quite easily observed, no, there is at the base the what do you call place for conduction has been thickened. So, from here you have almost things which run instead of parallel, no, slightly inclined and all that, this is easily understandable. And you see this is almost normal to this bend, and then depending on the method of manufacture and all that. So, you have two fans here, this is made black and this is some other thing. Something which you may appreciate now is that you have seen these last two fins, this and the other two fins are not exactly like the fins which are the other way. So, because they are also used for mounting, we can't afford to have anything mounted here. We have a problem because serviceability is a serious issue. So, when we keep this what do you call this air circulator here and then in line, because right now you need to what you call play around a little with it. One thing you will notice is, when you want to access this, you should be able to remove it without any problem, or in the case of hot plug-in, whole thing you remove and then supply something else. Something else which is very real is, if you see the base, can you see the base here? It is mounted onto something, maybe a chassis or something else. The thing is, this also aids in cooling. When you do not have too much surface area and you do not have all this, now every little bit what we have here, we should be able to make use of it. So, the Rensburg's correlations are very valid. So, here is, I mean I will kindly read it along with me. We have examined three modes in great detail. In engineering practice, cases where modes are combined simultaneously, radiation is not a significant factor, but to achieve best result, we should calculate the importance of each mode. For example, heat is conducted in parallel paths from junction to the case. Heat is then conducted from leads to the circuit board and from the case to a heat sink. Simultaneously, the heat in the leads and the heat sink is convected to the air and radiated to the ambient environment. This is where I try to point out, I hope you had a chance to look up the golden dragon LED or the Luxion power LED, which is mounted on a star heat sink. One of them is, most of those LEDs have a copper slug the bottom, so that you can attach it to it. Another is the leads or the tabs themselves conduct away heat, and in the case of the small things, you have no other choice but to have the heat dissipated via the printed wiring board, and on the printed wiring board we have copper. So, there is some way of making use of that slug in the middle and also making use of these what you call leads. It is very good for us. Okay, so, just as an example, instead of my showing you and asking you a question and answer saying how do you do it, I suggest you look up again, look for golden dragon LED, also Luxion, Luxeon, the what you call 3 watt LED with a heat sink. There in their application manual, everything is been given very well. Same thing is covered here, saying heat in the leads and the heat sink is convected to the air and radiated to the ambient environment. In the case you have a device like a single in chip or TO220 or various other things, we have lot of parallel paths. So, only way to make up for the parallel paths is to solve the problems of combined mode, set up a resistant network. We can graphically examine the paths of each mode for simultaneous, parallel and heat transfer. So, both are given simple solid or stationary fluid, where T1 is greater, heat transfer. We have seen this earlier. This is simplest what you can talk about in the conduction mode. Basically in conduction this is the simplest, and in the case of convection we also have, again everything has been to make us very convenient, everything has been made into a lumped heat transfer coefficient in convection, and there is an area and a temperature difference. Same thing, even this is about including a lot of shielding factors and totally, finally you have the total area, and then you have all this various type of thing and the temperatures, where thermal resistance in radiation is given here, in convection is given here, and conduction, K is conduction, this is convection to make it this thing. You have indeterminate number of individual materials, the rate of heat conduction is, they have tried to make it into a large equation. Delta T is the overall temperature difference across the entire composite, we often call it a potential temperature. We describe the thermal resistance. So, you have material A, B, C, and then by just joining these resistances of different materials, we come out with this sort of equations. So, we have an A and a B and a different any other material C and nothing, it is just by adding it is obvious, stating the obvious. We can rewrite the equation saying total power is temperature minus all the summation of all these things. Flow of heat is proportional to the temperature potential. From the basic understanding of series heat flow and resistance, can determine the characteristics of parallel heat flow through different materials. So, we know that the total rate of heat flow through two different materials, more comprehensively of each of the thing so on. So, only difference here is we have two paths here. You have seen this, we have a material here and a material here, a path here. Typically, where does it occur? It is not as if these numbers are thick like mineral insulation or your house insulation, or I keep giving you the examples of the domestic refrigerator. It is more like thin small cross sections of the order of millimeters and less. The case of chips are all hundreds of microns, that is about 0.1 millimeters. In the case of our slide chips, it is a little higher, and in the case of when you are coming to sub racks and when you are coming to actual racks, dimensions are a little slightly bigger. Thicknesses are usually of the order of 1.6 to 2 to 3 millimeters. So, if you see my heat sink also here, the thicknesses are slightly different. So, I have a heat sink, thickness here appears to be around 3 millimeters, then the whole thing is mounted on another plate. So, here comes the design compromise again. Do you directly mount it on a plate? If you mount it on a plate here directly, and if it is a conductor, you need to isolate the devices here, and you end up with a bigger problem. You understand, any small thickness here is going to cause a lot of problem. Instead, why not mount the device directly here with only a, without an insulator, apply enough pressure and directly, especially when you have things like a power diode, stud diode, you have no choice but to directly mount it here. If you mount it here, because of the direct potential difference, the amount of flow, what you call heat, the heat flowing inside will be much better inside. Thermal resistance comes down drastically, and you will be forced to isolate this at that point. So, this one, instead of directly contacting the external what you call world, you can probably have an insulator here, and then you join it here. Now, we have the both the advantages and disadvantages of how do you model this, how does heat start here, go all here, spread all the way here, and go also into the small thing, and how much of it is related directly, how much of it will come out, which seems to be our important factor. Got it again? This is where the source of this different materials and different choices are there, which is talking about. So, we have a thermal circuit in which two parallel resistors are there. If you go down, for the number of layers in series is the thermal resistance of the nth layer is the overall temperature difference. Similarly, since everything has been reduced to a simple heat transfer coefficient, there is an area involved and there is a heat transfer coefficient in each mode. Similar way, if you want to have both conduction and convection, okay, this is a convective heat transfer, how you attach all these things together and from a hot gas to a cold gas through a plain wall. This is typically, I told you about the panel mounted air conditioners. If you have to have a communication rack, sometimes you have no other choice but to remove usually the rear panel. If it is a closed rear panel, you remove the rear panel and then put this directly panel mounted air conditioner on the back. The air conditioner thickness, the big ones are about 200 mm, the smaller ones are maybe around 150 mm, this is 150 mm, 200 is about this much, and then the width is usually 400 mm, height can vary up to 2 meters, that is 6 feet. So, you put it at the back of the thing, and there you have a working fluid on the outside and then you have a working fluid on the inside. Other than this, you also have all the walls freely conducting also outside. So, if you have a wall thickness, you have a hot side and cold side and how these things, all these, if you know the actual property of the materials, you can easily find out how these things work. Okay. So, and then you have several parallel paths, hot gas to a cold gas through a plane wall showing a parallel path for radiation. Seen that, no? The moment something is hot, you have a little chance of a radiation also going through. So, you can have radiation and convection in parallel. So, since these are a matter of equations, again it is more like a handbook material, you probably need to get back with your specific case and try to work on these things. We come to the final overall thing, saying the combined simultaneous radiation convection, total area of heat transfer and so on, eventually overall heat transfer coefficient. Overall coefficient is used to describe the result of multiple convection coefficients of a single value. Common form of heat transfer used in exchangers is transfer heat from a fluid with higher temperature to lower, and the fluids are separated by wall. If you know that the wall is plane and there is only convection on both sides, we can find the heat. These are all very routine things everywhere. No, we end up with delta T and these thetas. Describe the flow heat only in terms of a temperature potential and transfer of each section in the heat flow path. Some instances it may be helpful to describe the heat flow single value in terms of resistances. Rewriting the equations gives directly delta temperature, area and U. Okay. Area UA is best should be stated in the problem to avoid uncertainty. If the chosen area is small, it may not reflect the overall value, instead for local value. We can describe the overall heat transfer coefficient of the outside area as a 2 by equation. So, these things go on and on and on and on and on. Okay. So, it is for you, since it is a handbook type material. We have several tables here which describe from the appendix. Okay. So many of these things are mentioned here in the appendix, saying as a huge appendix which is which gives data relating to most values which are likely to face. Air at sea level atmospheric pressure. So, we have thermal conductivity and kinematic viscosity. Similarly, water at sea level. So, again you have thermal conductivity, and then you have fluorocarbons which are part of the refrigeration system. So, so many of these correlations and thing, and about the K and these parameters which have been used in the earlier equations are all listed out in this appendix. So, you see here very commonly we have these 60 and 70 series aluminum which are meant for hard, strong. So, you can see your what you call performance bicycles, occasionally you have these what you call aircraft things and all that, no, they all form under this 5000, 6000 and 7000 series things here. But one thing, the compromise seems to be basic thermal conductivity. This is a soft simple what you call aluminum, and this could be variants with more and more zinc and what you call silicon and magnesium and zinc combinations. So, well, I am sorry, silicon and magnesium combinations with aluminum. As you improve the things here, the very hard ones have conductivities only as half of the soft aluminum. Similarly, we come with various types of brass and bronze and copper here. You have seen this. Things like this, C12200 and all that, they form under the category called FRHC, fire refined high conductivity copper. Next time you get a chance, open one of those Pentium or the main CPU chip in a computer. I am sure you have enough electronic e-waste computers. You open it and then you will find the fan, underneath you find the heat spreader, and if you turn it upside down, sometimes in the heat spreader you will see the material in the center has been bored out and a core of copper has been pushed inside. Why that is required is aluminum itself and the way it is configured is not able to take away heat at the rate at which we want the conduction to improve, unless the whole system will fail unless you have the highest conductivity of copper. So, copper like this, these coppers are used very pure copper materials there. To start with, they are very soft, and then you see conductivity is very high. Then if you go down, you find the things which we like, and of course gold you cannot afford it except in the case of a few, what they say, maybe where corrosion also is important and things should not degrade, electrical conductivity should not degrade with corrosion, that places gold are used, but very thin layers, maybe submicron layers. So, as we go down, you notice that we still can't beat copper. So, as we go down, we have all these interesting, very interesting materials, rather material properties which probably come across. Now, we come to the little, what do you call, I will seal, no? Well, I won't say it is a sad part, it is a reality part. Reality part is what we commonly call sheet metal is there to stay. So, sheet metal usually comes as this carbon steels, mild carbon steel. So, the main advantage of it is the overall price is low, easy availability, and because of its inherent toughness, it gives a pleasant appearance and does not get dented easily, which is the, and in a given thickness and weight, even today it is a good choice. That is the reason your cars, your car panels continue to be made with simple embossed or formed sheets, sheet metal. It is often zinc plated. Okay. So, in the roll form itself it is zinc plated, after that fabrication is easy, and one more thing related is all sorts of operations can be done easily, and finally eventually even painting is easy. Painting, various types, electroplating and so on are easy in ferrous materials. This is where we end up with, whether you like it or not, these carbon steels continue to be used. Very close to it is cast iron. Cast iron is used in some special conditions, but in this case we are not talking about direct application as much as we are talking about the thermal properties of it. If you go here, you see that basic stainless steel and all that, they are quite good in it. But then I am sure several of us have come across 304 stainless steel, which is again commonly used. The advantage of this 304 is that is the one you see everywhere. You see everywhere, all the shining things you see, probably dining stuff and all that comes with some variants of these things. So, the advantage is that it is not affected by atmosphere, and it does give a slightly good appearance to it. Then the disadvantage is heat conductivity is low, and sometimes these are also used as spring materials. So, this what you call appendix does not have the spring materials characteristic, So, if you see your battery contact or if you see any of your things inside a connector, they are not generally made with this, but if you take a spring, you have your usual AA cells and you have a spring at the back. So, it is nothing but it is a drawn wire, probably piano wire, 0.9 to 1.2 millimeters diameter, and it has to carry current and occasionally it has to carry heat. This is where your problem comes. Added to that, we have a problem of dissimilar metals, which is probably the reason why most of your portable equipment, if your what you call TV remote does not work, what do? You bang it or open the back and then try to roll the batteries, or take it and rub it and all that. The issue is the moment you have any dissimilar metals, it will form a electrochemical cell, which will lead to so many other problems. So, the main problem is you still have thermal conductivity is low. So, you have various properties people play with. While that is well known, what is not known at all about is the thermal properties of plastics. As of today, unless you actually apply it or make an experiment, these last figures are only indicative, because all the time big companies like BASF or Roman Haas or all the what do you call people who work on plastics, they keep formulating and making new things. So, there is a thing called ABS, we also have called nylon ABS. Similar types of materials are used in your normal commercial equipment as well as a bumper in your car. So, but obviously the car bumper has very good fantastic physical properties. So, not only its impact, it gives you a controlled crushing, which will take care of the what do you call various crash tests and all that. Now, coming back to our thermal aspects of it, you have this is the acetal copolymer. So, so many of these things, they are all very special things. Acrylic is all your windows, whether you like it or not, your what they call polyglass and Roman Haas what they call plexiglass, all of them are acrylic. Then you have cellulose acetate, all these things problem is the conductivity is not very good. It is real. So, how do you take care of it? Sometimes it is desirable, as in the case of our switches and so on. So, the switch does not feel hot when you press, you may even feel sparks and all coming, but it does not get hot. The domestic household switch, it has to take away heat. Luckily, inside the actual heat carrying elements are probably brass, and the contact point is probably brass which is coated with silver and so on and so on. So, the combination of these things, the heat has to be transmitted. In spite of our best effort, when it starts, switches will not be giving any heat. In due course, they will slowly develop a small resistance. With high current, heat is developed. Same it is in the case of our things like transformers, which we think are passive, actually they are generating a lot of heat, they are active in generating heat. So, we come to these things like epoxy, IC molding epoxy. Wouldn't have been lovely if we had a proper conductive epoxy, thermally conducting and electrically insulating. People are working on it. I do not know whether they are still using it or not. In those cases, while it is okay, you see I am wearing this fancy watch. I am sure some of you will know what this fancy watch is. It has fantastic properties, like it has a magnetic property, and then there is a separate rubber cushion here, and when I remove it, see the way whole thing is actually a stainless steel strap. I do not know how they have done. When I say stainless steel, it does not stain. Thing is, it is still magnetic. So, I will notice it. Martensitic is generally magnetic, austenitic steel is not magnetic. You see this, and more than this, the wonder comes at the bottom. Okay, I have a sensor here. There is a sensor in the middle. There are two LEDs. Something is blinking, and it's actually something very very active, and it's a wonder. And you can charge it. And the whole thing is doesn't cost anything. The original, I think I got it gifted, and it cost around 15,000 rupees. That may be around 200 US dollars. And the clone is available for 1,000 rupees, 999, which is nothing but $15. That is a lot of this thing. And you see that this is expected, I expect that I will carry it to the grave with me. Not that I hope to pass off soon, but then it is going to last a long time, and then usually waterproof and splash proof and all that. Now you see here, the really good ones have no choice but to make it in metals, and only a small layer, see even whole case is here is metallic only the critical portion they have made it out of plastic. They make it out of plastic, all that series parallel combinations are important. You see here typically these things are used. Then we have the another what is taken as a wonder material. We have two things, polycarbonate and polypropylene. Now everything you see, polycarbonate has advantage of that is a little transparent. Things like your blender jars, things like your other things are all made with polycarbonate. But very peculiarly it is scratch prone. Acrylic gives you a nice smooth surface, but it has other issues with it. So probably need to consult more and more things like this. So we have polyethylene, this is the stuff with which your plastic buckets and mugs and all are made. Then we have polypropylene. PVC is the material by default. Wherever you go, you have PVC stuff. We next come to thermophysical properties of ceramics. I am not very, how do you say, I belong to the old school. I have really no idea how these ceramics are used, except that I also, like you, have been reading about it. So I will avoid, except to say that we have fantastic, you see here, cubic boron nitride seems to be having tremendous amount of thermal conductivity, much better than aluminum, copper and those things. 6 times that of aluminum and maybe 4 times that of copper, which is very good, almost as good as film diamond. Then we have the other things. I do not know, they have not given the silicon and silicon carbide. This is a little, how do you say, I do not know how to use this information, but still in the case of gas, the temperature, conductivity, I am sorry, coefficient and so on are all given here. Very rarely, I mean, it is used only as a mass flow rate. So I have no experience in interpreting all these things, except that is a textbook information. Inside, if you see, reference has been made to these things. So common things is probably you have hydrogen, then you have common air, then of course is nitrous oxide. So you have so many of these parameters related to this. I will gloss over these things because I have no idea about these various things. Some other time you work it out. So we have this stuff about critical temperatures, effective temperature characteristic, force potential, specific heat at constant pressure to specific heat and so on. You can, air is based on combinations of these things. So, this is probably the end of this appendix, and the end of this thing what I wanted to talk about. Next lecture I would like to talk about the Peltier element design guide. Once again it is taken from Meerstetter. Meerstetter has a huge collection of stuff about Peltier element design guide, saying how to estimate the heat loads, how to choose a Peltier element. To me it still looks like a novelty item, but not necessarily a practical item. So, I will stop this session here, and next session which I talk, I will exclusively talk about this devices with Peltier cooling based on system overview, saying whatever it is. So, thank you.